Good afternoon, my fabulous chemistry students. Video number 5, periodic table. Today we get digging into the states of matter. So when we are done watching this video, we need to understand the three phases of matter, and of course how we're going to depict them in a diagram. So there are three main states of matter, right? And the we're concerned with in this course, and what we're going to kind of delve into a little bit, is the interaction between of the molecules. This is going to set us up for, of course, the three different states of matter in the periodic table itself, right? Because there is solid, liquid, and gas in there. So we're going to delve into it a little bit so we can get there. This whole at STP, that stands for standard temperature and standard pressure. They are in your reference tables in table A. We normally go with Celsius and atmospheres. This is a kilopascal, kPa, and K is kelvins. Kelvins is the most important measurement in temperature that we can use when we do calculations, because it does incorporate all of energy. So let's get into some definitions real quick. Solids, most example, carbon. Okay, most elements are solid at standard temperature and pressure. They have definite volume, definite shape. So think of the wooden block that we did in lab. It had a volume. You measured it. Does the volume change? No. That's what makes it definite or fixed, you can call it. Its shape doesn't change unless I physically change it, like run it through a grinder, right? Liquids, little l. There's only two elements, bromine and mercury, one metal, one non-metal. All right, Br2, and that should be a subscript 2, my bad. Br little 2, cursive L. Bromine, liquid, it's diatomic, we'll learn later. Liquids have a definite volume, and what it does is it takes the shape of its container, but it's confined by its volume. So let's think of Mr. Milks' coffee cup. When Mr. Milks is about halfway done with his coffee, right? It has a definite volume. I could measure it. It doesn't change as long as I can stop drinking it. But it does take the shape of its container, but of the entire container? No. I mean, it doesn't take up the entire mug anymore because I only got half of a cup of coffee left. But it does take up the container where it is able to. Okay, what its definite volume will let it. And I think on the next one you'll kind of understand why when we get into gases, what I'm getting at here. So gases, H, hydrogen, nitrogen, oxygen, fluorine, chlorine, and all of the noble gases are, gases. Except example, neon. They have no definite volume. They have no definite shape. Ooh, that's weird. Shape. Sorry about that. I'm not making a new one. Definitely, they take the shape of their container. So think about a gas that's, say, in the room. The room is full of a certain amount of air, right? Can I shrink that amount of gas if I could shrink the room? Yes. Yes, I could. The amount of the number of molecules of air would not change, but I could make it take a different volume. So that's what we call compressible. All right. The fact that liquids have a definite volume, that makes them incompressible. Now we're all very happy that liquids are incompressible, mostly because that's like, say, how our brakes work in our cars or in the bus on your way to school. You press the pedal, the liquid gets a plunger on it, the liquid moves, it moves another plunger to apply the brakes. If that liquid was compressible, the brakes would never go. Also, shape of their container. The air in the room takes up every nook and cranny of the room. Okay, it disperses. If I were to be in a smaller room, it would do the same. If I were to expand the room, it would expand. So the volume and its shape are completely dependent on the container that's holding it. Has nothing to do so much with how much of it there is. So here are some particle diagrams that we can show of a solid, a liquid, and a gas. You'll see that a lot of times with the solid, what I will do is I will draw them. I do like that they're ordered. A lot of times what I'll do is I'll leave space here to show that it's not taking up the container. Where this one in the middle, the liquid, the pieces are a little bit conjumbled, a little. See how they're going overlapping each other here, right? It's not showing the overlap, but you can tell that they're overlapped. But the most important piece is that it's taking up the whole thing. If your liquid doesn't go from edge to edge, we have a problem. Now the gas, this goes all over the place. These things are moving around based on how hot they are, but see how it takes up the entire container. So that's what we're looking for when you start drawing these things. Diatomic elements. They're by themselves, they're what we call unstable. So they pair up in order to fill their valence shells. They do have perfect sharing. We'll get into that later when we get into bonding. You just need to know which ones they are. So let's see if that's on the next page. Yep. So they contain two identical atoms. There's 7 of them. You can use the 7-up trick. I call it the 7H club. 7H club, or you can do, well, let's do the 7H club first and we'll talk about it. So H, of course, and then if I start at number 7 and make a 7, see how that green forms a 7? So nitrogen, oxygen, fluorine, chlorine, bromine, and iodine are all diatomic in nature. We will never find them by themselves. They always hook up. Okay? So here they are listed. The little 2's mean there are 2 of them. Okay? And of course up to H. So there's one other way that I learned how to do this. I don't know. I bet 7H is probably going to be the best for you. But there's one other one. It's called Hofbrinkel. That's how I learned it. So hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. Hofbrinkel. However you remember it the best and whatever works best for you, you just got to know that these are what we call diatomics. Diatomic, another vocabulary word we need to know. I always used to like to fantasize that Einstein named his dog Hofbrinkel. Allotrope. This one is on the test every year. One of two or more different forms of an element in the same phase, but with different formulas or physical. It gives us physical and chemical differences. So carbon is the one that's always given to us. So I'm going to do that one first. Graphite is carbon that's in your pencil. It's actually not lead, it's graphite. Versus diamonds. They're both just carbon, but the diamond gets a different structure based on the pressure putting on that carbon, and it actually, the molecules change physical location and become diamonds. Definitely different properties. Graphite is brittle, writes with it. Diamonds are one of the hardest substances we know of. There's also oxygen. In this case, this will be the different formulas because O2 is oxygen and O3 is what we call ozone. Again, it's still just oxygen, but these are what we call allotropes. So more vocabulary terms. On to practice. You've got the whole video to go through and watch again if you need to get you through this, or just with the notes you took in the video to get you through. We can now talk about solids, liquids, and gases. We can talk about allotropes, and we can talk about the 7 diatomic elements, all from this one little video. Be well, and I'll see you tomorrow.